Good morning, everyone. So what would you guys like to talk about this morning? Any topics or? Yes. Sure. So let me point to one of the equations of the Bohr model. So these are the equations you get with your test. And so when we use the Bohr model, we're kind of getting at equations that look like these two here. We can calculate a wavelength using the Rydberg constant and the two n values. We want to, if you use this equation, you may not really get the difference between a high n versus a low n. The idea of the Bohr model kind of shows us that we have the n equals 1 level, n equals 2 level, n equals 3. These energies are getting closer together as we go upward. And so we'll show the first 5 levels here. And so then if we go downward, say we have a molecule in the n equals 5 level for H, then we can lose energy by the H atom as we lower its energy level down to 4, 3, 2, or 1. And then the 5 to 4, 5 to 3 transitions, really low in energy. Those would fall like in the infrared region, being relatively low in energy. We saw that the 5 to 2, this would be a UV photon in terms of emission. The 2 to 1, this would be not UV, this would be visible. That was 1 to the 4 in our visible region. And then the 5 to 1 would be a really high energy UV photon. And so we get emission from high states to low states. If we wanted to do the opposite, if we wanted to go from n equals 1 to 2 or 1 to 3, et cetera, upward, we have to absorb energy that would be equal to those amounts of energies, but now being absorbed. So you shine a light on the H atom and it can absorb those photons that exactly equal the difference of energies between their energy levels. And so what we want here is to plug in our two n values, or we can use the equation here, which calculates the energy as a function of n for the hydrogen atom. And so you could plug in, if your final state was, say, like if you want to calculate the difference between n equals 5 and 2, so let's say you were trying to calculate the emission for n equals 5 to n equals 2, then you could plug in your final state n value, you could plug in your initial state n value, take the difference there, get that delta E, that's the energy that the H atom's losing, that's the energy that goes into a photon, and then we could calculate with an equation like this one here. We could calculate the energy of a photon. We could also write, though it doesn't appear that they give this one to us, hc over lambda is the energy of a photon as it relates to the wavelength. So they give us E is equal to h nu. We know from the speed of light that nu is equal to c over lambda. So we can just sub in for nu here to write this equation here. So if we get the energy of our photon, we can relate it back to wavelength. Of course, we could have just plugged directly into this equation here too and put, a 5 and a 2 in here. And I always forget which one's the 5, which one's the 2, but just the difference is only a minus sign. And so if you calculate a negative wavelength, just know that the 5 to 2 is emission, the 2 to 5 is absorption. And so that's kind of like a basic thought on how to use Bohr model. Now, some of the questions you tend to see are then, relatively speaking, compared to, say, the 5 to 2 transition, would the 5 to 4 transition emit a photon of lower or higher wavelength? So if we're looking at this transition here, the 5 to 2, and comparing it, say, to the 5 to 4, the 5 to 4 is a much lower energy transition, which would have a greater wavelength. So the 5 to 4 transition has a greater wavelength of emission, not absorption. If we're comparing the 2 to 5 absorption to the 4 to 5 absorption, then the 4 to 5 absorption would be of lower wavelength absorption. So again, light's emitted high to low, light's absorbed to go low to high. And one of the things you learn from the Bohr model is how precise you can be when you have one electron and one proton in the nucleus. Once you add more complexity, you add a second electron, we don't have simple equations like this that we can use. Conceptually speaking, probably more likely to where we're going to go. The test is pretty short, so we can't give you too many long math problems. So the conceptual side is comparing two transitions, which one has the longer or shorter wavelength. And just remember that as you go to longer wavelength, you go to lower energy. So that's why high wavelength, higher wavelength from visible, goes to the infrared, then the microwave, then the radio frequency. Radio frequency has wavelengths along the order of 1 meter. A nanometer range for visible, so 4 to 750. Okay, other topics? Yes? Yeah, so I don't think you're going to have to see visually the F orbitals. So let me add a slide here. And so when you look at the L value is telling you, S shape for 1, P shape for 2, D shape for 2, and then F shape for 3. So you have your S, P, D, and F shaped orbitals given by the L value. And so probably not a topic for the test, but if you were asked about planar nodes or angular nodes, that's just coming from this quantum number here. And so the shape here just shows you have no nodes for the S. You have one of these planar nodes, so you can imagine like a plane through the nucleus of the atom for your P shape. For the D shape orbitals, you get sort of 2 planes of symmetry, so you can imagine like nodal planes bisecting 2 axes. And then you would just have 3 of those planes for F orbitals. So and this is meant to kind of like cut into thirds, so you can imagine having a lobe here and here. So something that looks kind of like 3 sets of lobes where you just have 3 planes of symmetry through those nodes, but it's still kind of a planar orbital, if you will. So the orbitals are generally all planar, existing in one plane, other than perhaps if you picture some of those ones like the dz squared that has the ring. Do I expect you to know like the dx squared minus y squared by picture which one's that orbital versus the dxy, dyz? Probably not that level of sophistication, just that the d orbitals, 4 of them look like this, 1 of them looks like this, and then this one has the plane kind of through that donut ring. And so one of the d orbitals kind of looks like a p orbital, but it has that extra ring. Again, we're not going to probably show you the f orbitals and get you to picture them, but there was some that had like a lobe and then like 2 sets of rings that kind of were pretty funny looking, if you recall. So that's kind of what the f orbitals look like. Now it takes an n value of 4 to allow there to be the first set of f orbitals. So the first time we have an f subshell is the 4f. In terms of the periodic table, we only see 4f and 5f orbitals within elements in their ground state configurations. So, and then we don't finally get to the 4f until right after the 6s. So like the F block, where it is the cerium to lutetium. And so we don't get there until you go cesium, barium, and then we're going down through the F block. So go 6s to, if you think of the order of filling, you can almost like, again, look at the periodic table, tells you the ordering, 1s, 2s, 2p. I don't have the slide that's, but you get 2 elements across, so that's your 1s, 2s, 2p because there's 6, 3s because there's 2, 3p because there's 6. So you're just kind of like labeling here 2p, 3p. So this would be the 4p here, but we don't get to the 4p until we get across the 4s, the 3d, and then the 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p. So I mean, like this might have seemed tricky like last week, but hopefully you kind of get this pattern. Now, so I don't know if we're going to throw you an element like that's in these ranges here, because those are pretty uncommon to encounter anyways. But you can sort of see the pattern is that if we had to do, like, let's just crazy enough do the very last element of the periodic table, oganesson. And so OG, like at 118, would just be the nearest preceding noble gas, radon, which is 86 electrons here, 7s2. Then we get all the way across the 5f, so 5f14. Then we get all the way across the 6d for 10. Then we get all the way across the 7p for 6. And so, the F's only go 14 across, the D's only go 10 across, the P goes 6 across. And I'm just kind of literally just looking at the ordering of those elements. If we add all these up, if we add up the 86 plus 2 plus 14 plus 10 plus 6, I'm not going to do the math, but that would equal 118 as like a double check. So when you do your configuration, just count up all the electrons. It should match how many electrons that element has. And we're only doing configurations of elements. We're not worrying about ions in this chapter, so don't worry about the configurations of anything with a plus or minus charge. And then lastly, if we ask you for a configuration, it's always going to be the ground state configuration and the expected configuration we're looking for. Like, I'm not gonna throw you an anomalous configuration without telling you it's anomalous. So like if you see an element and you're like, if I were to ask you for chromium, let's say, which does have an anomalous configuration, chromium's right here. It should be a 4s2 3d4, but remember, it turned out to be a 4s1 3d5, so it moved one electron from an S into a D for some reason. If I say for chromium, like even just saying, tell me it's anomalous configuration is tricky because some of the anomalies aren't entirely crystal clear. So I would have to tell you an element's anomalous and I have to give you some clue, maybe tell you how many unpaired electrons the configuration had that would help you figure out what the configuration was. So if I ask you for a configuration for some element that you might think has an anomaly, like if you look at palladium ends up being one that's anomalous. I probably wouldn't expect you to know it, but it turns out it's a 4d10, or a 5d10 instead of a 5s2, 4d8. And then nickel, you might think would do the same thing, but it's completely normal. It's the 4s2, 3d8. So if I ask you for a configuration, I'm just asking for the simple expected configuration, not anything that might be one of those weird anomalies. Okay. There's a hand over here. Yep.
In the recessional credit she was talking about, like off-balance principle.
Yeah, like that's not in our book. But what and I briefly talked about the off-bow principle previously in the notes a little bit. So let me get into that on the next slide. Upon that, I had seen that was in her notes, and I was kind of thinking, that used to be in the older versions of like the textbook that we use. But this principle, you get it from the periodic table too. But the idea here is if you were to write out the orbitals that are allowed by like N and L values, so meaning like I can't write out D for 2p because you can't have a 2D orbital. Like we stop at 3D for N equals 3, stop at 4f for N equals 4. If I carry this on for a couple more, 5s, 4p, why am I going back to 4? So 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, that the order fills like downward this way. So we go 1s, then 2s, then 2p, then 3s, then 3p, then 4s. But the periodic table is telling you this too. So when you get to 3p and you're like, does the 3d come next or does the s come next? Off-Bell's principle is like, oh, if you just align these orbitals this way and kind of zigzag your way through, then you go to the 4s, then 3d, then 4p, then 5s. But I don't think there's any empirical reason why this works other than that it happens to work. So this is what Off-Bell's principle is kind of getting at, is you just fill then 4D across to the P subshell, then back to the S. But you're getting this in the periodic table too. So if you just literally look at the order of the elements, you'll get these configurations here. And so then if we were to continue just for the 7S, 7P, then you could cap off kind of the remaining configurations. And so through this here is like the last known element that's been thus far discovered. Physicists are trying to bombard nuclei with all kinds of particles to try to create elements in the kind of 8th row of the periodic table. So it'll be interesting to see if they ever figure one of those out. But it'll be of almost no practical importance though. So, other topics or questions? Yep. Yeah, so like how do you find the quantum numbers for, or just how do they all relate together? And so like sometimes like if we said you have, like some sort of an element that has an electron in a 5D orbital, like what are some of the possible, or what are like what do you know about the quantum numbers here? Well, the N value is the 5, the shape is from the D, so that's L equals 2. And so then the range of values for M sub L, we don't know it exactly. If I just said an element has an electron in a 5D subshell, and so this whole thing here is a subshell, all the possible L values are all the subshells that are possible with a given N value. So if you were to look at N equals 5 and how the range of L would go from L0 to 1 to 2 to 3 to 4, that this would all encompass the N equals 5 shell. So when we say shell, we mean everything that shares the n value. That's possible. But a subshell is just one of those subshells. So we'd have the 5s subshell, the 5p, the 5d, the 5f. These aren't so important, but if you think by numerical value, you can have what would be, I guess, the 5g functions. We probably wouldn't ask for anything beyond what elements use on the periodic table, but that's what the n equals 4 would be relating to. So the 5d would have an L2. The range of m sub l's would be -2, -1, 0, 1, and 2. And it's the fact that you have 5 values here that says that you have 5 orbitals within the 5d subshell. So you can get up to 10 electrons in because each electron can have an m sub s of plus or minus a half. And so if we were to show you like a configuration of something in the like 5D row is pretty big, so you're getting into something maybe like tungsten or osmium. So let's look at element 76 for osmium. So this would be the preceding configuration of xenon, that's 54 electrons. So the configuration of osmium would be a xenon, and then just follow xenon to cesium and barium, the next 2 elements, and then they're in the 6th row. That's how you get the 6s2. So if you're like, I know it's an s2, how do I know the number? Just count downward, it's the 6th row, so 6s2. And then we have to go all the way across the F block, the first F block, so that's 4f14. And then when we go across the D subshell, that's where we come to, it's the 5th, or it's the 3rd D subshell, which would be the 5D. And then how many across do we go? Well, one of the ways you could do this, if you just think of adding these electrons, if we go 54 plus 2 plus 14, that's how many electrons I've distributed so far into my configuration. So let me do that math real quick. So 54 plus 2 plus 14 is 70 electrons. So I have 6 to go. So through here I have 70 electrons. I was supposed to have 76. So I have I have to have a 5d6. I could count across, but the counting across is tricky because we just have to make sure we count all the way across from from lanthanum, hafnium, tantalum, tungsten, rhenium, osmium. But the fact that lanthanum is where it is in the periodic table sometimes confuses us. You might also take note. Okay, and so then if we were looking at like a subshell here, so our 6s2 spin paired electrons, it's like our n is 6, L is 0, m sub L is 0, that's the only possible m value. So if you're looking at this particular subshell, you can break the values down. N is equal to 6, L is equal to 0, the only m sub L is 0 that's possible. The m sub s for those electrons, one's plus a half, the other is minus a half. So that's those 2 electrons. And so then we have the 5d subshell, or well, let's do the 4f because that would come next, 4f for 14. So we have 14 spin paired electrons. And so we have an N of 4, L of 3, and then the M sub L. It doesn't necessarily go in this order, but one of them's minus 3, one's minus 2, one's minus 1, one's 0, another one's plus 1, plus 2, and plus 3. So we get those 7 M sub L values, and each electron is either plus or minus a half in those subshells. Okay, then we finally get to the 5D. 2, 3, 4, 5, 6. And it's Hund's rule that I'm using to spin pair those electrons and maximize the use of space. And so coming up with 4 unpaired electrons. And because we have 4 electrons that aren't balanced with the spin down electron. And then the M sub L values minus 2, minus 1, 0, plus 1, plus 2. So I have 5 M sub L's being used, N5, L2, etc. And so each electron in our multi-electron atom has have a unique set of 4 quantum numbers, the L, the N, L, M sub L, M sub S. And so principal quantum number size is the N, the shape is the L, the projection or the number of the orbitals that are possible for a subshell is from the M sub L, and then spin up or spin down is M sub S. Other questions or topics? Yeah. Yeah, that's probably not a question we would throw you on the test. I mean, I think it's a good question. I think the answer would be for sure these 6 and then these 2. Why those two in the 6s? Well, we count the valence as the outermost shell, and we usually include anything in a lower subshell that's unfilled. And so I would take the valence count to be the 2 that are in the outermost shell and plus the 6 that are in the unfilled D subshell. So as soon as you fill a D subshell, I wouldn't count those towards the valence. But again, I doubt they'll throw that to you on a test. It does get a little confusing because it's like zinc is a 4s2 3d10. Does it have 2, 10, or 12 valence electrons? I think the best answer is 2. So once you fill a D subshell, you stop counting it because it is in the lower subshell. So like calcium 2, if you look at carbon 4, but again, probably not something to worry about too much for the exam because it is nuanced. Other topics? Yep.
Did you do like finding the enthalpy of a reaction given the enthalpies are separate, like different reactions?
Oh yeah, like Hess's law, yeah. All right, so this might be a little bit of a simpler example on this. Like obviously the more reactions we give you, the more challenging a Hess's law problem. But if you're trying to figure out what's the enthalpy for this reaction, 2 iron plus 3 Cl2 gas goes to 2 FeCl3 solid, and we give you these 2 reactions here, no matter how many reactions we give you, I think the easiest thing to do, or the way to kind of approach this problem, is to try to look for something like, so in our overall reaction we have iron here, and there's 2 of them. And so can I find iron in just one of the reactions down here? So if I'm examining my 2 reactions, I have iron solid here and only there. And so if I were to look at, like let's say the Cl2, I see the Cl2 here and here. It's in 2 different reactions. So starting with Cl2 is probably not the thing to try to balance first because it's in 2 reactions. I don't know how to get them to add up just right. But I do know because iron's only in this reaction here that I need to double everything because I have to get 2 irons. So the only way to get 2 irons when I add these reactions up is to double that first reaction. So I have to double the delta H. And so I could write that out. So if I write out 2 Fe solid plus 2 Cl2 gas goes to 2 FeCl, but it's 2. I need 3 here, not a 2. So I'm getting closer to what I need. And so then this delta H would be equal to 2 times minus 341.8. So delta H of that reaction is minus 683.6. And that's in kJs. Now, let's take note of the not symbol. I got a couple questions. What does it mean by not? Sometimes like that's just the way that I like to use to signify that it's a delta H of reaction. And the not just means under standard conditions. And the standard conditions are so big, like the only one that really matters is you assume the reaction goes to completion and the coefficients are moles. And so whenever we say that this is the number of kJs, that's specifically for the 2 moles of iron reacting with 2 chlorines to go to 2 FeCl2. Okay, and so then the next reaction here, if I look at FeCl3, I need 2 of them, and I have 2 of them over here, but just on the wrong side of the reaction. So if I flip that reaction, I put the 2 FeCl3 over here. That's a solid. And then I have the 2 FeCl2 now as a reactant, and a Cl2 as a reactant. That delta H is plus 1, well, I flipped it. So if I flip a reaction, so flipping it's like multiplying by minus 1. So I need to invert the delta H. So my delta H should be minus 115.4. And so the reason why you need to see how you need to manipulate the equations is so that once we manipulate our delta H's and change them to what they need to be, I just now add them up. So I just add up these 2 values here because I'm going to add up my 2 equations. And then I can cancel out the things that are on both sides. So imagine the delta HF of FeCl2, 2 of them on the product side are counterbalanced by 2 of them on the product side. So the enthalpies of those compounds cancel each other out. And then the chlorines add up to the right number of 3. So I get 2 Fe solid plus 3 Cl2 gas goes to 2 FeCl3 solid. And my delta H should be minus 683 plus minus 115.4. That looks like the minus 799. Okay, so Hess's law it's just a puzzle. So just try to start the puzzle with one of the things that's in one of the reactions, get it balanced onto the right side in the right quantity, and then kind of go from there and balance the other substances. Other topics? Yep. So there was a question on one of the questions from Dr. Wynn's packet, Dr. N's packet from her review on the titanium plus oxygen reaction in the bomb calorimeter. I wouldn't worry about the concept of bomb calorimetry. So if you see any problems in talking about a bomb calorimeter, I would not worry about those problems. There's one in my notes too. I think I allude to it on the next slide when we get to it, and you'll hear about it in a moment. But on the topic of bomb calorimetry, it is a similar type problem to coffee cup calorimetry, but I would only worry about solving the problems of a reaction taking place inside of a container that's open to the atmosphere, where we're going to set up the Q reaction is negative Q surroundings, which is a very fundamental relationship, which is just true for anything. So Q system, negative Q surroundings, and then the surroundings is the solution that the reaction taking place in. So the surroundings of the reaction is just the solution, and then you end up describing your Q reaction as a negative MCS delta T for the solution. And so there's a couple examples that we work on later in this packet here today. So like I had this problem in my notes, and I was going to say to not worry about this problem here too, because we pretty much said to not worry about bomb calorimetry this semester in terms of it being asked on exams. So worry more about solution or coffee cup calorimetry. So the coffee cup calorimetry problems, or where you have something being added to water, the solution temperature is changing, and then you're looking at the heat of the reaction as being the negative the heat of its surroundings, which is a fundamental relationship that's always true, that the heat of a system is always the opposite of its surroundings. The surroundings is what we track the temperature of. So we have the negative Q of the solution. So the solution is the surroundings. And then the solution is described by negative MCS delta T. So we have this here for the entire solution. So you have the mass solution, CS solution, delta T solution. And so from that, you can calculate Q reaction. So the heat change of the reaction is negative MCS delta T. And then once you have a problem with this that you solve, you then usually have to say, well, what's the delta H and like kJs per mole for the compound? And so then you're looking at taking your Q reaction, dividing by, usually like thinking whatever the limiting reactant is. And a lot of times there's only one reactant. It's like you're putting one compound into water, or maybe you have two different components you're putting into solutions. Whatever one is the one is in lesser stoichiometric quantity. So you put the limiting reactant here, usually in grams, and then you just multiply by the number of grams per mole. And that gets you into joules or kJs per mole. Okay, and so the best calorimetry problem in this packet is number 4 here. And so this here, you're putting silver that's hot into water in a coffee cup calorimeter at 22.9 degrees. The temperature is initially 26 the temperature rises to 26 degrees. What is the specific heat of silver? This is kind of similar to some of the problems that we looked at, but the idea here is that the heat of the silver is negative heat of the water. So silver has a lot of heat. It's going to lose heat. Water is going to gain heat. So I just need a minus sign in front of one of them. And so then silver would have its MCS delta T for the silver equal negative MCS delta T for the water. And so we know the mass of silver is 20 grams. We don't know the CS of silver. That's what we're looking for, times the delta T of silver. So 26 is the final minus 81.3 degrees from its initial temperature. And then that's equal to negative mass of water. So 121 grams of water times the CS, 4.184 joules per gram Kelvin, and then times the final minus initial, 26, final minus 22.9. Does allow me to say you don't need to double convert. If you want to take a delta T in degrees C, it's a delta T in Kelvin. You don't have to take if I do this math, 26 minus 22.9 The delta T for water is 3.1 degrees C. I don't want to add 273.15 to that and double convert it into Kelvin. So this is equal to 3.1 degrees C, which is equal to 3.1 Kelvin. Think of, if you want to convert to Kelvin, convert the 26 to Kelvin, the 22.9 to Kelvin, take the difference, and you'll agree that it's 3.1 Kelvin. And so our units here cancel just fine. And so the only thing I don't know is CS. So let me take 121 negative times 4.184 times 3.1. So I have negative 1569.4. And now the only units left are joules. And that's equal to 120 times parentheses 81.3, or I'm sorry, parentheses 26 minus 81.3. So that's negative 6,063. Negative 6,636 times CS. And that's the number of joules here again, because we're canceling out the grams and the degree C. And so I can calculate my CS here just by dividing by negative 6,636. So my CS looks like about 0.25. So 1569.4 divided by 6,636. So that's 0.236. And joules per gram degree C is the same as joules per gram Kelvin. Yeah. Yeah, so so when we just have the silver going in, we have the heat of the silver versus heat of the water. So it's because I just have Q silver, Q water, water's MCSLT for water. If you go to the calorimetry columns where I'm putting like a solid into water, and then those are turned into Q reaction versus Q solution, then you have MCSLT solution. And so that's the reason in those ones you use the mass of the thing you add to the water plus the water mass. And so it's just kind of like, did the math boil down to our two substances on either side? Or did we have like the reaction versus solution where the solution is the entire surroundings and we have to take into account both? And so when you have a reaction taking place here, you just have silver being added. There's no physical change taking place, or no chemical change, I'm sorry, taking place. But if you had something like dissolving into water, like you're putting ammonium nitrate into water, calcium chloride, something that's dissolving, or you have even a chemical reaction taking place, it just becomes a question of what's the Q of that specific reaction we get from negative MCS delta T of the solution, and then we relate that back to, well, the kJs per mole of some substance. So the de Broglie wavelength, sometimes we go lambda D, but I think if you look in the equation sheet, it just says lambda is H over MV. So this is how you can calculate the wavelength. I'm going to make sure that looks like a new symbol, that this is the velocity of the particle in meters per second. You need the mass of the particle in kilograms, and Planck's constant in joules times second units. A joule, something that we don't maybe realize all the time, is that a joule is a kilogram meter squared per second squared, is exactly what 1 joule is equal to. So that's why we want the mass in kilograms, and then we want our velocity and our seconds to cancel here so that we get our wavelength out in units of meters. So we get our wavelength in units of meters if we just plug everything in SI units. And so probably not a problem you're going to see numerically in terms of using this equation. We use it just to show that for a ordinary sized particle like a baseball, that there's no real wavelength. When we throw a baseball, it's not oscillating like a wave like a photon does. And then if you think of an electron that's being fired across a potential or spinning around a nucleus, that it is going to have like a wave-like behavior because, in particular, because of what we see from this approach here, that the wavelength we calculate for the particle is on the order of its trajectory. It's on more of the order of the size of the spinning around a nucleus. And so I think the idea here is just we're seeing that the electron behaves like a wave, more massive particles don't. And then we also then see from the uncertainty principle, which an equation looks like this: delta x times m delta v must be greater than or equal to h over 4 pi. This is the uncertainty principle. Again, probably not a problem mathematically you would have to worry about solving, but it's just showing you that you can't simultaneously know the position and the velocity. Your ability to know those precisely at any given moment is fundamentally limited by quantum mechanics through this fundamental equation. And so it just gives rise to orbitals. So the wave particle that you don't know where it is kind of then says, what about probability distribution? So these two approaches together kind of lead to the idea of orbitals. And then quantum mechanics, the Schrodinger equation, that being a better way of trying to understand where particles are and some of their properties than, say, even like the Bohr model. So the Bohr model actually is incomplete. Even though it works very well to calculate the energy level differences for the H atom, it leaves a lot of questions unanswered that then we can answer with quantum mechanics. Other topics? Yeah. Hello, this is a re-record from this morning's lecture because I forgot to record on this slide. But I had gone over these two problems during the review portion of the class, and we were talking about standard enthalpies of formation. So anytime you're asked to write a formation reaction, so the formation reaction of a compound is you form the compound as a product. So you want only the product on the you want only the compound of interest on the product side of the reaction. You want there to be only 1 mole. So even if you need fractions in the reaction, you leave the fractions on the reactant side and you just leave 1 mole here. So you never have more than 1 mole on the product side. And then you want the reactants to be the elemental forms of carbon and hydrogen. So that would be H2 for hydrogen, carbon, carbon solid, graphite. And so then C is wrong because that's not the elemental form of carbon. And then the elemental form of hydrogen is not H atoms, but H2 molecules. And so what I would know is that the elemental forms that are gases are H2, N2, O2, F2, Cl2. These are our diatomic gases. And so these are all gases at room temperature, along with the noble gases as monoatomic gases. We also know carbon solid graphite is the natural state of carbon. So graphite solid for carbon. These are the key non-metallic elements I would know. I mentioned that Br2 is a liquid, I2 is a solid. I doubt the test would really require you to know those two details, but those come up. But I wouldn't worry about the other non-metallic elements like phosphorus or sulfur. I wouldn't worry about the metalloids and their physical states, but then know that metals are solid with the exception of mercury, which is a liquid. So now continuing along to the next question here, we have a reaction where we can find the delta H of the reaction using the standard enthalpies of formation of the products and the reactants. We just want to account for stoichiometry. So we'll go 3 times the CH4. We'll take 1 times the CO2, and then 2 times the water. We got to take into account our coefficients. And then we subtract, so the sum of the products, and then minus the reactant, so minus 4 moles times minus 110.54 for the CO. And then the H2, we have to know is 0. So delta HF of H2 is 0 here. So sum of the products minus the reactants. I didn't know what the answer was. We didn't mathematically evaluate it in class. So I'll just say, if you need to, double check the key. For this question here, we're using bond enthalpies. This equation's on our equation sheet. You're going to see it on the first question of your exam. But our delta H of a reaction can be approximated by taking the sum of the bond strengths of the reactants and summing those up, and then subtracting the sum of the bond strengths of the products. But the equation's given, but this is a weird one where it's reactants minus products, because you're saying how much heat does it take to break that bond and break this bond
and then we're going to make this bond here, and then we're going to make that bond there. So we're leaving these bonds here intact. So those bonds aren't changing, so I'm not going to break those because they are exactly CH bonds in the products, but I'm breaking a CH and a Cl bond. And so the CH bond is 413 kJs per mole. And then, so 1 mole of that bond, then 242 kJs per mole for the Cl2 times 1 mole. So the mole cancels. So that takes 655 kJs to break those two bonds. So breaking bonds is always exothermic. And then we're going to subtract the bond enthalpy of the products. And so we're going to sum up the products bond enthalpies. And so breaking this bond and this bond would take, so think of how much energy it would take to break those bonds. So breaking those bonds, carbon chlorine is 328 kJs per mole times 1 mole. And then plus the other bond, summing up the 431 kJs per mole times 1 mole as well, so the mole cancels. And so summing these up, those are equal to 759 kJs. So it takes 759 kJs to break the bonds that we are trying to make in the product, so we get back minus 759 for forming those bonds. So forming those bonds exothermic, breaking the bonds in the reactants endothermic. So endothermic to break the bonds, exothermic to form them. So the difference is minus 104 here if you work it out.
So let's look at 3 and 4. We'll wrap up here in chapter 6 and then get into some new chapter 7 material here today. So number 3 says a laser emits energy with an energy of 525 kJs per mole. What's the wavelength of the light? And so the wavelength of light comes from the equation E is equal to h nu equal to hc over lambda. And so the energy of a photon is equal to hc divided by lambda, but this is just for one photon. So that's just our photon energy equation. So I need to think, what's the energy of just one photon here? So I have to think, well, what's one photon energy from 525 kJs per mole? I just think 1 mole of photons would be an Avogadro's number of photons. My H is in units joules, so I'm going to want to convert into joules. So a kilojoule is 1,000 joules. And then I want the energy of just one photon. So 1 photon, mole cancels, kilojoule cancels. So that's my photon energy here in joules. Should be really small. So I get 8.718 times 10 to the minus 19 joules. And then I just plug that into as my E of my photon, hc over lambda. So I can solve for lambda by taking hc divided by this energy of our photon. So I take 6.626 e to the minus 34. You can check your equation sheet. You get Planck's constant. You get the speed of light. So if you forget those values, you can look them up. And now this is going to come out, so units joules times seconds times meters per second divided by joules. So the joules canceling, the seconds are canceling. Only unit not canceling is meters. So I get this answer out in units of meters, 2.27 times 10 to the minus 7 meters. They wanted in nanometers. So I just need to multiply by 10 to the 9. And that tells me that this is 228 nanometers. So light with a wavelength of 228 nanometers has a pretty high energy in kJs per mole. This is why UV light's hazardous or dangerous to be around, is that it has enough energy, it can start breaking bonds in your eyes, it can break bonds in your skin. So harmful to look at, harmful to encounter in terms of potential skin cancers. So high energy per mole. So from the photoelectric effect, we see that this amount of energy is capable of causing events to take place that require that amount of energy or high, or that amount of energy or lower to take place. And so when we see a question like 4, copper metal must absorb radiation with a minimum frequency of 1.15 times 10 to the 15 hertz. In order for an electron to be ejected, that's relating to its ionization energy. Then what wavelengths of light can cause this electron to be ejected? And so this is a frequency that's a nu value, so C is equal to lambda times nu, or nu times lambda. And so then we can solve lambda just by taking the speed of light dividing by the frequency. This is just an inverse second. And so if we take the speed of light, 2.998, e to the 8, divide by 1.15, e to the 15. That looks like 2.61 times 10 to the minus 7. And same conversion into nanometers is 261 nanometers. And so when we go to light that has, now let's think about greater or less than here. So when we want the frequency to be at least 1.15 times 10 to the 15 hertz, because the energy of our photon is equal to h nu. So we want to be at that frequency or higher in order to cause an electron to be ejected from our atom. If we then think about E equal to hc over lambda, we want to be at that wavelength or lower. So when we go to lower wavelengths than 261, we go to a greater energy. So we want to be at wavelengths less than 261 nanometers to go to a greater energy